Yes? Yes? Oh, okay, it's coming. Okay. All right. Can you see this?
Yes.
Okay. Right. So, so this work is with my former student, Hataishi, who's here today, Pierre-Francois Dutot, who's in Grenoble, Rafael Ferreira da Silva at USC, and myself, I'm in the University of Hawaii. And the topic of the talk is scheduling of scientific workflow applications onto batch scheduling platforms. So, we have a scientific workflow, which is depicted here on the left. That's actually a workflow from a real application that many of you are familiar with. It's called Montage. It's from astronomy, where every vertex is a task and every edge is a data dependency. And we want to run this application on a batch schedule cluster with some background workload, meaning there's competition for the compute nodes, and we have to submit jobs to the batch queue. Like everybody here, of course, is very aware of this. And so what our objective is to minimize the max span of the workflow execution, meaning the time between the first job submission and the last job completion. We make several strong assumptions. Some are strong, some could be removed easily. We assume the workflow is static and that we know the dependency structure. That's still the case for a lot of production scientific workflows. Task execution times are known and include both I/O and computation based on previous benchmarks of the workflow. Each task executes on exactly one compute node. So unlike the talk we just heard from at the, I was able to catch the last talk in the previous session. The tasks are non-parallel jobs, so they run on a single compute node. And then the batch scheduler, as done in production, imposes a limit on the number of running jobs a single user can have. Okay, so those are our assumptions. And to decide how to schedule the workflow onto the system, we have to answer two questions. First, how should the workflow tasks be partitioned into batch jobs? And second, when should we submit those batch jobs, right? So the idea is going to say, we're going to submit one batch job for maybe 5 workflow tasks. And then once that's done running, what do we do with the next set of tasks? And so if we provide answers to both these questions, then we define a workflow scheduling strategy. So there are two very obvious baselines right away. One is, I'm going to call it one job. And that's a very trivial one. We put all the tasks in one batch job. And when do we submit it? Well, right now. Right? So that's just submitting your entire workflow as a single job. And so that has several drawbacks. It has high wait time, right? Because the job could be massive. And so then you may be stuck in the queue for a long time. And also it has poor resource utilization. I'm putting it in parentheses. I'm going to talk about resource utilization at the end of the talk. I'm going to ignore that for a while. The other baseline is the other extreme, where we say, well, each task is its own job. And when do we submit the job? Whenever the parent jobs are done, right? So those are two strategies anybody would come up with in a few seconds. And that one, the one task per job strategy is not great either. It has cascading wait times because while the task is running, competing jobs arrive from other users. And so then next time you submit when you submit your next task, you may have a lot of wait times. And also you're throttled by the per user job cap. If your machine says you can only have 16 jobs in the system and you have 1,000 tasks that can run in parallel, then you're throttled at running only 16 of them at a time. So those two approaches are simple, but they have pretty clear drawbacks. And so the question is there anything in between those two extremes? One thing that people seem to mention in practice, at least in the literature, it's mentioned quite often, is a very simple level-by-level approach, where you say, I group all the tasks in the same level of the workflow, meaning all the tasks that have the same top level in a single job, and I submit those levels in sequence. And so that seems to be used in practice, and it's mentioned, as I said, in literature, but it's not clear whether it's a very good compromise between the two extremes. Maybe it is, but it probably depends on the workflow and on the workload. As far as we know, the only previous work that has tried to answer this question, is there anything between those two extremes, is a paper from 2009 by Zhang, and they don't name the algorithm, so I'm just going to call it Zhang. And let me tell you how they work, but here the outline of the talk. So first I'm going to explain how Zhang works. Then I'm going to show some evaluation of Zhang we've conducted. And then we're going to propose an alternate approach called GLUME. And then I'm going to show results for that one and conclude with future work. Okay. So the Zhang approach, how do they answer the first question? How do we partition tasks into batch jobs? what they do is they submit sets of contiguous levels as a single job. So it's not level by level, it's groups of level by groups of level. And what they do in their original algorithm, they ask for as many nodes at the maximum level width, which is a problem of the algorithm that, in fact, we end up fixing. Because if your workflow is too wide, then Zhang just fails. Right? And then the big question, of course, is how many levels, right? So I'm at the beginning of the execution, do I submit the first level as a job, the first two as a job, the first three as a job, right? And the way they do this is they consider all the options and they gather wait time estimates from the batch scheduler, right? Most batch scheduler, you can say, if I were to submit a job that asks for this, how long would I spend in the queue? Right? And so those estimates are not prediction. There's a big literature, of course, on batch queue prediction. Those are simply based on the current state of the queue, and we have no idea what the future state of the queue will be or what jobs are going to be coming in. And then so that gives us an estimate of the wait time, and then we estimate the runtime based on critical path, and then we try to pick the best option. So it's actually very straightforward. There are a lot of details in the Zhang algorithm I'm glossing over. I'm happy to answer questions about its details, but here is the high-level idea. So here is the workflow, and Zhang just said, what if I submit the whole thing as a job, right? So this rectangle is the job. And then I ask the batch scheduler, what would be my wait time? And in this example, which is completely made up, the batch scheduler says 18 hours. And then how long would I run, asking for some number of nodes? And again, Zhang just asked for the maximum possible number of nodes given the width. And then let's say the runtime of this, the length of the critical path, would be 10 hours. Then I say, well, wait time 18 hours, runtime 10 hours, and I compute the ratio, which is 1.8. Obviously, I want to have a low ratio, right? Very low wait time, very high runtime. If ratio is greater than 2, there's a heuristic here that Zhang says, forget it, it's not worth it. I'm going to do one job per task. So I go back to one of the simple extremes, right? So first, I evaluate the one job extreme. If the ratio is greater than 2, then I say, forget it, I'm going to the one job per task extreme. But then I look at the other option. How about just submitting the first level, right? So that's the red job there. And let's say that this is 2 hours of wait time, 2 hours of runtime. Compute the ratio, it's 1.0. And it is lower than 1.8. Therefore, I keep going, and I look at the first two levels, the blue jobs. And let's say for this one, it's 3 and 6. So the ratio is 0.5. I keep going, and I consider the first three levels, the purple jobs. And let's say for this one is 4.5, 7.5, and the ratio is 0.6. That's an increase compared to 0.5. So then Zhang stopped and said, therefore, we're going to submit the blue job. And so the first job will be the first two levels of the workflow. Okay, so that's how Zhang answers question 1. This is a pure heuristic. There are some justification in the sense that, of course, we want a low ratio, but there are many other choices here that could be made. Okay, so then Zhang submits this job. Question 2 is when, okay, now that we decided how to group the workflow tasks into jobs, when do we submit them? And this is kind of what one might expect, right? The main idea is you submit the next job right when the previous job starts running, right? So we could say when it finishes, then we're guaranteed that everything works well, but then we don't do nice overlap of wait time and runtime. So I think on the picture, it's pretty clear. In that picture, time is going from left to right, of course. Job 1, and the wait time is in the red polka dots. So we submit job 1 for maybe the first 3 levels of the workflow. And at time T2, job 1 starts running. And so that's the green there. At that time, we invoke Zhang again. That said, now we should submit the next, let's say, 4 levels. And that's job 2. And job 2 starts right when job 1, job 2 is submitted right when job 1 begins execution. And those first 2 jobs are the perfect case where the wait time of job 2 is exactly the runtime of job 1, which of course never happens, but that's what we would like to have. And that way we have perfect overlap of runtime and wait time. Right? But of course, there are 2 other situations. Maybe the wait time of the next job is lower than the runtime of the previous job. So that's what happens to job 3, where we submit it, but turns out it spends less time in the queue. So then it idles for a while, and that's the yellow zone. And I'm not going to go into details here, but there's a technique used in the Zhang algorithm called a leeway that says because my wait time is probably going to be lower, I need to ask for more time during which I'm going to idle and then start running whenever my parent tasks have completed. Right? So that's the idea here. And the other situation is your wait time of the next job is longer. So that's what happens for job 4, where then job 3 finishes, but then job 4 is still in the queue. So then we have idle time because we don't have anything to do while job 4 is waiting in the queue. Right? So again, as I said, the algorithm is quite intricate. There are a lot of details, but hopefully this gives you a good overview of how it works. And so how well does it do? So there are results, of course, in the Zhang paper. And those results are a little bit strange in a way. They quantify mostly wait time and not the make span, which is what the user cares about. And also the algorithm in there has a lot of strange limitations. In fact, even some bugs we end up fixing. You can look at the paper for more details. In particular, the fact that if the workflow is too wide, Zhang just fails is, of course, not acceptable. In practice, you want to say, well, I should be able to run 10 independent tasks on 5 nodes, just double up, right, one after the other. So we did some experimental evaluation of this algorithm for 36 workflow configurations from real-world applications listed here. And you're probably very familiar with those if you've done anything with workflows. Different scales in terms of number of tasks, 50 to 250 and 500. And then an amount of sequential work of 100 hours, 500 to 1,000, which is actually really low. I'll come back to that. And we call those short, medium, and long, even though long is really not that long at all in the current landscape of workflows. Of course, we use workflow traces from the parallel workload archive, and we replay them with conservative backfilling. And we implemented a simulator using several technologies, the range simulator, which builds on top of SimGrid, and the batch scheduling simulator. And all the code is, of course, open source and linked off the paper. And what we do, we pick one of those workflow configurations, one of those traces, and we replay 400 different workflow submit times, each, if I recall correctly, 1 hour apart. Right? So what if I submit my workflow now, an hour from now, an hour from now, and so on. So that gives us a lot of data points to evaluate the algorithm. So this is pretty standard practice for evaluating those kind of algorithms. And we compare Zhang, in which we include many fixes and enhancements, and in particular, the fact that if the workflow is too wide, then Zhang will not just abort, but in fact, run by doing some kind of list scheduling of the tasks given the allocations on the nodes. Level by level, where we use wait time estimates to pick the best number of nodes for a job. One job, where also we pick the waste time estimates. We use the waste time estimates to pick the best number of jobs, and 1 job per task. Right? So in Zhang, they compared, in the original article, they compared the algorithm to 1 job and 1 job per task, but their 1 job was very naive. It always asked for the maximum number of nodes, almost guaranteeing every time an outrageous wait time. So instead here, we allow 1 job to use fewer nodes if it thinks the make span is going to be improved. And so we obtained a lot of results, and I'm not going to go into a lot of details here, but this is the typical graphs where on the y-axis we have the workflow configurations, and then we have on the x-axis, and on the y-axis we have the average improvement relative to Zhang, meaning if we are above the 0 line, we beat Zhang by some percent in terms of make span, and below we are beaten by Zhang. So what we find here, these are results for one of our traces and job traces, and for 128 job cap, meaning a user cannot have more than 128 jobs in the system, which for these examples means that 1 job per task is not throttled. The workflow width is lower than 128. And so what we find here is that 1 job per task is often equivalent to or better than Zhang. Right? There's only one case here toward the end. For some reason, my mouse pointer isn't showing, so I can't move around. But basically, 1 job per task looks really good in these results. 1 job sometimes better, which is a little bit surprising, but often much worse than Zhang. And we expect that because there is no throttle of the number of jobs in the system. So Zhang often defaults to 1 job per task, and in this case, the 128 job cap doesn't impact it. And level by level is sometimes better, but often much worse. Okay, so this is only one set of results. Obviously, we have tons such results. And then if we set the job cap to 16, then 1 job per task should not be doing well because it's going to be throttled in terms of the parallelism it can achieve. And that's what we observe. Right? On this picture, One job per task is often much worse than Zhang. You can see here on the right, especially for the medium and long workflows. But then one job is often equivalent or better. There's only a couple of cases where it's worse. And level by level is, kind of a mixed bag, but often better than Zhang. So obviously there are a lot of results here, and these were just one set of results to show you the type of graphs I'm going to show again a few slides from now. But when we look at all the results, the message is pretty consistent. Zhang is just not a clear winner over the baselines. When the job cap is low, one job does relatively well, overall better than Zhang. And when the job cap is high, then one task per job does relatively well, better than Zhang. Right? And Zhang is a very complicated algorithm. These two can be implemented without any thought, right? So it makes it doubtful that Zhang is actually worth it. Overall, level by level doesn't seem to be a right approach, even though that's the one people seem to be referring to in the literature the most often. And so the question is it possible to do better? Is it possible to use a non-baseline algorithm? Or should we just tell people, if you don't have a job cap, one job per task it is. If you have a low job cap, then just do one job and don't even try to do anything fancy. Right? So that's the question that came to our mind when we read the Zhang article. And there is one clear weakness of Zhang at the conceptual level, is that it does not attempt to optimize the make span at all. In fact, it does very local optimization of the wait time runtime ratio. And yes, a low such ratio is a good sign, but that is still not directly optimizing the make span. So maybe Zhang is not a bad idea, but it's not optimizing the right thing. And so that's what we try to do in our new algorithm. So at the surface, it looks a lot like Zhang. Of course, there are not that many ways of doing this. Like Zhang, we submit contiguous workflow levels as jobs. But unlike Zhang, we decided to never default to one job per task. That way, GLUME is absolutely agnostic to the job cap. Right? At most, there are two jobs in the system. So therefore, we should work really well, regardless of the job cap. And the key idea, which I'm going to show in a picture, is that we assume we're going to run the whole workflow as two jobs. So we compute the best two-job schedule. Then we submit the first such job, and then we forget about the second one, and we do all this again. Right? So at every decision step, we assume there will be only two jobs, but then we forget the second one, and at the next decision step, we assume we're going to have two jobs again, and so on. So in fact, the workflow execution can proceed with many jobs, way more than two jobs. So here is a picture. Say we have a workflow with 10 levels to run on a cluster with, let's say, 16 nodes, right? And we're going to say we must use it with two jobs, J1 and J3. And so here is one option. I could say I'm going to run the first 4 levels on 6 nodes as job 1, and then the next 6 levels on 10 nodes. Right? So that's one option. And so what I would do, I would submit J1, and for that I can obtain a wait time estimates from the batch scheduler, which is the red shown here. And time, of course, goes from left to right again. And then I can say, well, those 4 levels on 6 nodes, how long do they run for? Assuming some list scheduling algorithm on the task and to the nodes, I come up with some duration. Right? So that's what I expect the execution of the first job to be. Then at the time when job 1 starts, I'm going to submit job 2. And here, I need to know how long that job will be in the queue. Now, that's a little bit difficult because I won't be submitting for a while. Right? I'm submitting it in the future, but we don't know what the future looks like. In fact, the job estimates we're getting could be very inaccurate as well. Right? I should have mentioned that. Of course, the red I'm showing here could be way off, right? Because it's only an estimate. But here we have to say how long will J2 spend in the queue when I submit it some hours from now. And that's a very difficult question. And as a heuristic to make things even worse, we say, well, let's assume we submit it now and ask the batch scheduler what it would be like now. And then assume that's going to be the same wait time we're going to experience in the future, which is, of course, not correct. Right? But hopefully it's close enough that we can do something. And then the batch scheduler tells us, if you submit a job asking for this much time on this many nodes, then you would spend 3 hours in the queue. And so we assume we will spend 3 hours in the queue later when we submit that very same job. And then that job runs some time. We know how to estimate the runtime. We know the number of nodes. We know the tasks. So we can use list scheduling. And so that gives us a potentially very wrong estimate of the make span. Okay, so that's one option. 4 levels on 6 nodes, followed by 6 levels on 10 nodes. Here's another one. 6 levels on 10 nodes and 4 levels on 6 nodes. Of course, here I'm just drawing it in PowerPoint, right? So, and so here's another estimate may expand. In this case, for instance, the wait time of the second job is lower, and so we need to idle a little bit in that Zhang-like leeway yellow area before we can run the tasks of the second job. And here's another one, and so on, right? And so basically what we do, very brute force, we just look at all the possible options, estimate the max span, knowing that those estimates could be off, and then we pick the one with the lowest estimated max span, and we say, go with that job, right? And that's the first job, J1. And we completely forget what we said about J2. And then when J1 starts, we invoke the algorithm again, assuming again 2 jobs for the remainder of the workflow. And so hopefully that made sense. And therefore, a workflow with n levels could be executed with as many as n jobs, right? At every step, we think it's only 2 jobs, but again, we only submit the first one. So that's the main idea. And the conceptual difference with Zhang is that we directly optimize an estimate of the max span as opposed to a greedy local optimization of the wait time to runtime ratio for a single job. Okay, so most of the results look like this. I'm showing results only with job cap of 16. Turns out if we do lower job caps, we look even better. And if we do a massive job cap, then things tend to converge and there's not much difference between the algorithms. Note that in production, a lot of the production systems have very low job caps. In fact, 2 reviewers of this work, when we showed them show these results with a job cap of 16, 2 reviewers of the paper said 16 is way too high, our system is lower than that. The lower the job cap, the more attractive GLUME is with respect to the other algorithms, because GLUME uses only 2 jobs no matter what in the system. So we're never impacted by the job cap. So we picked 16, which is a little bit higher to not make it so obvious that our algorithm, of course, beats the competition. And so those are the typical results. You can see GLUME in red, which is equivalent or better than Zhang and the baseline algorithms in all the workflow configurations. That's what most of the results look like. There is one case for the SDSC trace where GLUME loses, and we haven't been able to determine what feature of that trace makes it that it doesn't do a good job. That's left for future work. So I'm going to show aggregate results here that aggregate over all our configurations. And in some of the results, GLUME doesn't look great, and all of those bad results are imputable to the SDSC job trace. And again, we haven't been able to figure out why. So this is a big table. So how do you read this table? This means that this is the win-loss record of GLUME. So this means for medium duration workflow, so those that sequentially take 500 hours, what this means is that out of the 36 configurations, GLUME beats level by level 33 times and is beaten by level 1 time. Right? So it's a win-loss record. And because the algorithms are often very close to each other, we didn't want to bias the results here by counting as a win by 0.1%, right? So in this table, we pick that you win only if you're 5% better. The results are not very different if you pick 2% or 10%, turns out. It's just a way to filter out the tiny wins that are probably not meaningful, right? So that's why 33 plus 1 is lower than 36, meaning there are two ties where the algorithms are within 5% of each other in terms of max span. Okay, so that's how we read the table. So for long workflows, the win-loss record is perfect, meaning GLUME is either equivalent or beats the competition. In particular, it beats Zhang 14 times. And that's a really good result, especially because our so-called long workflows are only 1,000 hours, which is really minuscule compared to some production workflows running today. For medium workflows, GLUME mostly wins when compared to the 2 extreme and 1 job. It has a 10-11 losing record to Zhang, but 10 of those losses are for that SDSC workload I mentioned. And again, we have no idea why that is, and that's a very complicated investigation, as you know. Understanding features of batch workloads and how they impact scheduling decisions is, of course, not easy. And then for short workflows, so those are really ridiculously short, then it's a mixed bag, and GLUME beats one job and level by level, but it doesn't do so well compared to one job per task in Zhang. Turns out for these short workflows, you should just do one job per task because backfilling works so well that you're going to end up winning, right? So there's no real way to do much better than one job per task. And Zhang does well, but that's because it defaults to one job per task. So that's expected if your workflows are tiny. Yeah, one job per task works, right? The good result is really that as the workflows get long, then we have a non-losing record. And of course, people are in this game to do long, expensive workflow executions typically. So the summary of the results: GLUME beats its competitors, provided that workflow computational demands are high enough. And the way in which it achieved this, unlike Zhang, the previous work in this area, is that the partitioning of the workflow levels into jobs is to optimize the max span. And in particular, that partitioning allows it to outperform the one job approach. The results show that Zhang, in fact, in those cases, when the job cap is 16, Zhang is not better than one job, which is really sad because Zhang is a very fancy algorithm and one job is about the simplest algorithm you could think of. And as I said, for short workflows, it's just difficult to beat one job per task. And that's why Zhang does well, because it often defaults to one job per task, right? Our design choice for GLUME was to never do that default so that we don't care about the job cap, but for short workflows, it's a losing option. And again, I want to point out that we really try to show results that are difficult cases for us, meaning our medium workflows are only 500 hours of compute time, which is really, really small. Right? Production workflows on platforms today are much, much longer. In fact, even our long workflows are really not that long. And so, that's what we wanted to achieve, to do well for those very long, expensive workflows and not caring as much for the very short ones. Okay, so I realize I don't have a clock around, stupidly, so I have no idea whether I'm behind or ahead. But here I am at the end. So here is the future work. So I'll have several directions. So one direction, which personally I'm not really into, but I can see how it would make sense, is to allow GLUME to default to one job per task for short workflows. I mean, do we care about short workflows? I'm not really sure. But if we do, then of course, GLUME is not a good algorithm. Now, it's very easy. You can just say, hey, when based on some criterion, just default to one job per task. And that's what Zhang does. But the way in which Zhang does it seems very arbitrary. It's a magical number. When some ratio is lower than 2, is higher than 2, then default to one job per task. There's no real justification for it. So it would be kind of interesting maybe to develop a heuristic to decide when to give up on the fancy approach and say, you know what, the workflow is such that we should just do one job per task. So that's one direction. Again, I'm not sure how compelling it is because maybe we don't care that much about short workflows. Now, beside the max span, of course, a key metric is resource utilization, right? It's very easy to enhance all these algorithms, of course, to ensure. So I'm not talking about the utilization, of the cluster as a whole. I'm talking about given an allocation for a batch job, how much of those compute nodes do you end up using? Because since you're running sub workflows on those sub DAGs of tasks, there could be, of course, idle time. So it's very easy, of course, to enhance all the algorithms to ensure that when you're given a job allocation, you run your tasks achieving some minimum parallel efficiency, right? And so very easy for the algorithm to say, well, yes, I could ask for this many nodes for that much time, but turns out my utilization of those nodes won't be lower than 80%. Therefore, I'm not going to ask for that job. I'm going to ask for fewer nodes. Right? It's really unclear how this will change the relative results of the algorithms. We haven't done that. But as far as implementing this in the algorithms, it's pretty straightforward. And then if the workflows are very wide, then even a single level is an enormous job, right? And at that point, we probably need to split not only horizontally along levels, but vertically, meaning a level could be run as multiple jobs, right? So we could call that maybe vertical partitioning. And as far as I know, no one has really looked at that, and that could be very difficult unless you do level by level. But if you do groups of level with fancy horizontal partitioning, as well as fancy vertical partitioning, that maybe a lot of interesting, difficult questions arise, and maybe it's worth exploring those questions. Okay. So that's it. Again, I want to thank you, the organizers, for scheduling my talk in the last session. As I said, it's super challenging living in Hawaii, so some of us have to do it. So thank you for that. That's why I didn't have to wake up at 4 in the morning like for other conferences. And do we have any questions? And yes, it's me right here surfing on that slide. So because I could see that was going to be a question.
Thank you very much. I have one small question, but if someone else is...
I do have a question too, but you can go ahead.
Okay, I didn't quite understand. So you're scheduling workflows and using the parallel workloads archive. So you're using the data from the archive to set up the parameters of the tasks in the workflow? Or...
No. The parallel workload archive is used to simulate a competing users. So,
okay. Yeah.
So that the cluster is not dedicated.
Yeah. Okay. Then it's clear. Okay. Thank you.
Sure.
The question that I had is the method relies heavily on wait time prediction from the clusters. I don't remember. Did you do some work to see what was the effect of higher, lower average quality of those estimations on the performance of GLUME?
So we did some things. So the results I showed here are all with where the jobs. So we use conservative backfilling. So if every job runs for exactly as long as it said it would, then the estimates will be really good, right? Because it's conservative backfilling. However, the results I showed here are playing the trace from the workload archive where the jobs ask for some time, but turns out they run for much less. Or I guess if they go up, they get killed. So in fact, those results are for the inaccurate queue wait time estimates because the jobs came earlier, therefore there are backfilling opportunities and so on. We do have in the paper results where we pretended that the jobs in the trace ask exactly for what they need. So that would be the perfect case, okay, where there is no wait time estimate problem. For most of the results, there was basically no difference in the trend. The one difference was for that weird workload, SDSC workload, for which if we play that workload, faking the job request time to be perfect, then GLUME does as well as for everything else. If, however, we play that workload with the real wait time estimates, then GLUME fails, likely because from that system, turns out the wait time estimates are terrible, right? What we didn't do is inject, what we should do, maybe in a journal version, is inject a fixed amount of wait time estimate error to perform a sensitivity analysis to see at which point does it no longer make sense. But for 3 of our workloads, we use the real wait time estimates, job or runtime estimates provided by users, and those are way off. And we still didn't see any problem when wins are all over the place. In fact, all those results here I showed in this talk are only with a real runtime requests, which are way off, meaning the estimates of the queue wait times are not accurate, far from it.
Okay, thank you.
Thanks. Sebastian, do you think you can try again? It's weird. I hear my echo from Sebastian, but I can't hear Sebastian.
It looks like Sebastian's trying a different machine.
Hello? Do you hear me now?
Okay,
Yes,
We can hear
yes.
you
yes,
now.
we do.
Oh, wonderful. So now I've switched to a different computer. I'm so sorry for the delay. I apologize.
No problem.
Okay, I'll try to share my slides now. Can't share my screen. Okay. That should do, right?
Yes,
Okay, wonderful. So sorry again.
no problem. The floor is yours.
Okay, thank you. So I'm presenting here joint work with Christoph Kessler from Linköping University in Sweden, and also with Jörg Keller, also from Fernuniversität in Hagen. So this is the overview of my presentation. I'll give some remarks about the motivation, then there'll be some background information, and then briefly talk about temperature-aware scheduling and how we implemented that, present some of the experimental results, and then give a short summary. Now with chip fabrication technology advancing, the heat increasingly becomes an issue, and this, of course, has a negative impact on power consumption and may even lead to hardware failures. And the operating system governor can, of course, mitigate that to some extent, for example, by dynamic throttling. But since it usually has no knowledge about the application performance may then suffer, which in a way calls for user-level scheduling. And of course, from a more holistic point of view, you would also have to consider heat diffusion on a multi-core system, so heat flow to neighboring cores on the chip. The applications we have in mind here are streaming applications, where the input arrives in discrete packages over time, and then runs through the application. The example here is for an application with 4 tasks. You see the task graph on the left-hand side, and then on the right-hand side, how the application proceeds, where time goes from left to right. And each column represents a single round, a single time slice, where each task is executed, but not all for the same input. So we don't have any intra-round dependencies here amongst the tasks, which is important for the scheduler, of course. Now, if we have an application where a certain requirement regarding the minimum data rate exists, so for example, a camera delivers images at a certain rate, then this means we have for each of these individual rounds a deadline or a maximum length until which the task must be executed. And the scheduler has then several options to ensure this. For example, if the application allows for that, parallelization, or maybe frequency scheduling. And the target we seek to optimize here is then the minimization of power consumption, because that's will be beneficial with regard to the temperature. Now, the architecture we have in mind is a generic multi-core system where the cores are placed in a 2D layout. We assume we have an upper limit for the core temperature, and we further assume that we can individually frequency scale each of the available cores. We will make no specific assumptions about the power function, and the modeling of the temperature will be pretty straightforward here in the way that we simply classify cores as Cotter-Holt. Cotter-Holt, you could, of course, do this in a more fine-grained way, but this is how we started to do that. And we then have the according power consumption values. Of course, the heat diffusion also needs to be modeled, and we did this in a way that we could incorporate that in the ILP at the end. The application, as I've already said, would then be characterized by a streaming task graph, and we allow for multiple variants of tasks. That could mean different algorithms or different sets of parameters, maybe, where each of these variants can either be sequential or parallelized to some degree, but where the number of cores the task is executed on does not change at runtime, so this is determined in advance. The scalability for each task is then given by parallel efficiency functions for each of the task variants. When it comes to scheduling, then decisions will have to be made for each task on which variant to execute, the number of cores it shall run on, and the cooperating frequency. And all this must be done in a way that the constraints regarding the round length and the heat are kept, and then the optimization target would then be the overall energy consumption, which would then lead to the minimum heat production, hopefully. So the basic technique we employed here is crown scheduling, which aims to reduce the scheduling effort. And this is done by partitioning the set of available cores into groups. We see an example for 8 processes, and the core group structure, which is then created, where each processor has its own group, these groups 7 to 14, and then at each level going upwards, we would conjoin 2 of those groups in a way that the groups of the same level do not overlap, and then a task is not scheduled to an arbitrary set of cores, but to one of these 2p-1 core groups. Another point is then the execution order, which is fixed in a way that tasks are executed in order of descending width. So this would be an example here, where time proceeds upwards, and in the lateral we have the cores, and we can then see that first all the tasks are executed on all cores, and then the tasks that only utilize 4 cores, 2 cores, and then the sequential tasks, which means that we will not have to specify individual start and finish times, which again saves some considerable scheduling effort. Now, of course, we will then have to map the group structure onto the physical chip geometry. And this is an example of how you could do that. So there will be one group that contains all the cores, and then you will repeatedly partition the set of cores in a way that groups of the same size do not overlap, and all the cores in the group are physically neighboring indeed. So one other point is then that this technique will have to be extended to accommodate temperature-aware scheduling. And what we then did is we compared the integer linear programming approach to a heuristic approach, which you could also utilize for scheduling at runtime. Okay, I will briefly sketch now the general idea, all the technical details on the paper, but I don't think we'll have time to deal with that. So the general reasoning was that if we have some tasks that may produce a lot of heat, that could be large sequential tasks, which then imply that the cores they are mapped to must run at very high frequencies, consume a lot of power, produce heat, then this can, if you try to accommodate the deadline constraint, on the other hand, then lead to heat constraint violations. And the solution we found for that was that we don't map these critical tasks to a single set of cores, but to 2 core sets or 2 core groups with the crown scheduling technique, and then for each round switch the core sets. So we alternate the execution from round to round. And in order to well, not lose too much in terms of solution quality, we of course sought to integrate this decision on which tasks are mapped to an additional core set at scheduling. So to represent this in the ILP, essentially. And the implementation was then to map a task to a core group twice the size. So if a task should run on 4 cores, then we map it to a group containing 8 cores, so that we could alterate the execution from round to round there. And for each core in that group, we would define a body core where between these 2 cores, the execution switches over the rounds. And for each task, then we will add a new variant, which implies the body core execution. At runtime, then every core would just regularly execute the tasks which are mapped to it in every scheduling round, except for the hot tasks, which are mapped to twice the number of cores, which will just be executed every second round. Yeah, so 2 ways maybe there in which you can further generalize this approach. So on the one hand, you could provide the scheduler with more flexibility by allowing to choose body cores arbitrarily. So we will not have, let's say, core group 2. And if we employ the buddying technique, then the respective body group would be core group 3, because it does have the same number of cores and it's situated right next to group 2. But we may choose any group, and maybe even a group that doesn't have the same size. So there are more or less fewer cores in that group, or which may be in distinct areas on the chip. And of course, then we may have to factor in some penalty, which represents things like cache misses or data movement. But well, it still may be the case that you may find a feasible solution that way, or maybe even an overall better solution. But that would then be up to the scheduler to decide. And the same goes for the length of the idle phase the body core undergoes when in rounds where it doesn't execute a hot task. That you can also leave to the scheduler, and maybe you will in the end find better solutions. So we also implemented an ILP for these 2 generalizations. Okay, so I'll briefly talk about some of the experimental results from our scheduling experiments. So we did these with 2 applications, one merge sort application, where you can see the task graph on the left-hand side. So we had 15 tasks in this task graph in that kind of tree-shaped form. And the H263 encode application from the data flow benchmark suite. The task graph is here on the right, where you have 9 tasks and quite some control flow. What we then did for our scheduling experiments was to vary the round length, so essentially the deadline tightness, and the limit for the heat constraint. And then for all parameter settings that we examined, we computed schedules for these 2 applications via an integer linear program and also by a heuristic approach, which we also don't have time for now. And the central question was, can we see any effect of employing the body core technique when it comes to the number of feasible solutions? So can we produce more feasible solutions employing the body core technique compared to just regular scheduling under the temperature constraints? And we also examined how heat diffusion or modeling heat diffusion affects any changes in that regard. So we chose a multi-core processor with 16 cores here for our model, and we took the power characteristics of the ARM-Big Little because these were available in the literature, and the solver was the Gurobi solver and was run on a AMD Ryzen consumer CPU. So these are some of the results for the merge sort task set. We have on the x-axis the deadline tightness, so the deadline gets loose if we go right, and on the y-axis the heat constraint, which gets more restrictive going upwards, and the brown area then represents parameter combinations for which a feasible solution could be found with the regular cron scheduler under the heat constraints, and the blue area indicates solutions, feasible solutions that were in addition found by the scheduler employing the body core technique for the critical hot tasks. On the left-hand side, we did not factor in heat diffusion to neighboring cores. On the right-hand side, we did. And you can see that in any case, there are some cases where you can produce additional feasible solutions. Of course, if you do factor in heat diffusion, these cases are fewer because heat diffusion mitigates heat spikes on single cores, which might prevent feasible solutions in some cases. And this is pretty much the same here for the H263 encode task set. Looks a bit different, but yeah, more or less you observe the same effect. This is another experiment we did where we did not allow frequency scaling, so where the cores ran at maximum frequency for the whole time. And there you can see a pretty much more pronounced effect of the of employing the body core technique. So there are very few feasible solutions for the regular cron scheduler under heat constraints, but you can, yeah, for really quite some parameter settings produce feasible solutions here with the body core technique. This is one last slide with a comparison of on the left-hand side, the employment of the bodying technique for fixed bodies. So each core group is designated a fixed body core group. And on the right-hand side, you have the results for flexible body selection. So where the scheduler decides on which group is bodied with another group, and also decides on the length of the idle periods in rounds where the specific core does not execute the hot task it is assigned. And you can see that, again, you can squeeze out some more feasible solutions here in the top left corner. Okay, so in total, we have seen how you can energy efficiently schedule streaming task applications onto such many core CPUs where the cores are placed in a 2D layout under deadline and temperature constraints. And we have also seen that the temperature-aware scheduling, where we employ the bodying technique, leads to a larger parameter range where you can still produce feasible solutions. The heuristic approach, where we didn't talk about now, can then be employed when static scheduling is not viable, for example, when the application runtime may be too short. And you can also get some results here, but yeah, so no time for that. And well, the next steps would be maybe try more applications, although the results for these two were pretty similar, but maybe larger applications or, well, yeah, differently shaped. And then very importantly, do a validation of these results on a real system. I mean, we used the power profiles from a real system, but still this would have to be empirically validated in some way. And from a theoretical point of view, it would be interesting to extend this concept of bodying cores and core groups to different kind of architectures, especially heterogeneous architectures. Thank you.
Thank you, Sebastian. Do we have questions? I have a question, probably stupid one, but in those figures, sometimes the the difference between, yes, in these figures. So in some experiments, the difference between body cores, the amount of the area that expands due to the fact that you are using this body core technique is the improvement is significant. I mean, what was the word for that? Eligible space, or yeah, in this case, for example. So do you have some explanation why sometimes the body cores make a great difference and sometimes they still make, you know, better solution, but not so dramatically? Do you have some explanation for that?
Well, in this case, we assumed that frequency scaling was not available, so the cores ran at the maximum possible frequency, which then, of course, leads to quite some heat produced, and which makes the technique more valuable. So in the other cases where frequency scaling available, you already have kind of a tool to mitigate the heat problems.
Yeah, so it's well explained. Thank you. Do we have some more questions for Sebastian? If not, thank you once again. And it's unbelievable, but we can move to the last talk. If my calculations are correct, we will move to Chicago, I believe. And
hello.
Hello.
Hi, let me start sharing my screen. Sebastian, you have to stop sharing before I can share. Okay, thank you.
Sorry, just before you start, I must emphasize how grateful I am that every single paper was presented live. It's a great achievement, and thank you for that. Thanks to all of you. So the floor is yours.
Okay, thanks. Can everybody see my screen presentation mode?
Yes, we can.
Okay, thanks. Okay, so my name is Chaojie. I'm from University of Chicago, and my advisor, Andrew, is also here. So today I will be presenting our paper on scheduling challenges for variable capacity resources. So we have the power consumption in data center are accelerated just because some of the a couple of reasons. So one is the end of Dennard scaling have significantly produce increasing power density in the data centers. And then also we have continued rapid growth of computing, for example, the e-commerce, cloud computing, VMs, etc. And so all these will produce dynamic power management for cost, cooling, etc. in the data center just to save money or to improve their computation. So on the other hand, a lot of governments, so for example, here in the States, the government have been pushing a lot of pressure on reducing carbon emission in the data centers. So we have a lot of large IT companies that have making aggressive carbon emission goals. So for example, I think Google have previously been carbon neutral, which means that they buy green energy to offset some of their traditional brown energy to become carbon neutral. And companies like Google, they have pledged to actually be carbon free, which means that to use green power 24/7. And so this is a figure that I took from Google's commitment in their green energy. And a lot of people, we all know that all these hyperscale cloud data centers in Google, Microsoft, Amazon, etc. They have a lot of data analytics workloads such as machine learning jobs and etc. So with this aggressive carbon emission goals and also the increased computing demands, they have to either reduce power consumption or use renewables coupled with to enable more computation. And at another level, we also have a lot of studies on synergizing the load with the grid or using local renewables like solar or wind turbines to enable more computing or more power whenever the renewables are available. So with all these reasons, we are envision future data centers to have variable resource capacity. So how does the variable resource capacity problem look like? So in a traditional world, we have fossil fuel or reliable grid power and also some fixed price power that feed into the data center. And so we have a resource capacity that is a fixed horizontal line. And the scheduler will envision this fixed capacity for scheduling and assume it's going to be stable going forward. However, in the future where we envisioned there will be volatile renewable grid power or the highly variable power cost that will go feed into the data center. And different from a fixed horizontal line, we will have variable resource capacity that will vary over the time. And sometimes the scheduler wouldn't know in the future. So why would resource capacity vary? While resource capacity varies, it would impose a lot of scheduling challenges in the data centers. So if we look at one system performance example, which we will go back later in detail. So this, we look at, so the y-axis basically from left to right, it's a measurement of how volatile are the variable resource capacity. And so more to the right means more volatile variation, where the y-axis is a measurement of the system utilization. So we can see that as resource capacity become more and more volatile, we can see that there's a clear trend in the system performance to cost degradation to up to about 30% comparing to a fixed capacity scenario. And if we look at one of the variable capacity example generated by one of the causes that we listed over there. So the y-axis is basically a time series over a whole day where each bar represent the resource capacity at different time of the day, and where the horizontal line would represent the fixed capacity in a traditional data center. So to note that I think there's a few people previously asked, but over 100%, we are making assumption that data center have backup resource capacity or turbo boost mode that can temporarily go over the 100%. So we can see that as the time goes, the resource capacity in this example can vary significantly across all the ranges in time and also on short scales from interval to interval. So some of the contributions that we made in this paper, we formally defined the scheduling problem as the variable capacity resource management in data centers. We list a couple of examples of the empirical traces generated from various sources. We study the scheduling performance under the variable capacity in data centers. And we also provide a couple of promising results of the scheduling improvement that can be done. So back to the job scheduling challenges with variable capacity. We previously showed that variable capacity could cause performance degradation. So why would that be a challenge in the data center? So assume we have a traditional data center with fixed horizontal resource capacity. And now, if we are shifting from the fixed capacity to the variable capacity cases, so all the increase in the resource capacity would incur an underestimation for the scheduler that assume fixed capacity. And all this would lose opportunities in scheduling new jobs and improve the system utilization. And all the decrease in the resource capacity would causes overestimation of the scheduler. And while the capacity doesn't support the current scheduling jobs, that would incur significant job terminations or throttling. So with these scenarios and challenges, we propose several key questions. So the first is, how do current scheduler respond to the capacity variation? Second is, how can scheduler performance be improved in these challenging situations? And the third is, how should we best limit or shape capacity variability for performance and other benefits, such as carbon or power costs? So in order to generally understand the impact of current scheduler response to the capacity variation, we define 3 key dimensions of the variability. So the first, as we see on the right-hand graph, so this one is variability traces that I previously talked about. And so the first dimension is the dynamic range, which measures the minimum to maximum capacity that one variation could go up or go down to. Where the second measures the total variability structure. So we have a random walk, which measures the gradual, smoother type of changes. So between intervals and intervals, the changes are the same or gradual, where we have random uniform, where between 2 intervals, the changes can be anywhere within the dynamic range. And last, we have change frequency. So basically, this is the frequency of the capacity variation. So basically, how long each variation would last of the interval. So we will first look at a few empirical traces. So the first is a constant rate of expenditure. So we purchase power at a fixed rate, fixed amount of dollar cost per hour. So this is example power costs that we took from the mid-continent power grid. So including Chicago area. So this is the power prices of a day. So we can see that there are some low or stable prices, and there are a few price spikes. And this would be the resulting resource capacity that we generated from this by purchasing the power prices over here in a 200 megawatt data center. So we can see that as the price is stable, so this couples the dynamic market price to the resource capacity directly. And we can see that so for the resource capacity, there is a large variation of over 5-fold. So basically from 0.2% to 1.0 within short periods. And so just to mention, because the price could be very low or even negative, the variation potentially will be limited by the physical capacity that one data center might have. And next, we will look at one empirical variation from constant carbon budget. So similar to the previous dollar budget, we are now having carbon budget. So this is a grid's carbon emission rate that we took from the German power market. And so we took 1 day for the past 1 year because there could be seasonal or weekday periodic changes in the carbon emissions because of the renewables. So each line represents a day in a month. And so we can, and this is one example that we get from the resulting resource capacity of the same capacity as we showed earlier. So we can see that with the carbon emission rate, it has a smoother variation over the period that close to a random walk structure, because normally the renewable generation are gradual, unlike the price that will be quite volatile. So with here, we demonstrate that it has a smaller dynamic range of 0.65 or over, so to 1 in the data center, and the step size varies from small to large. So last, we will look at one example of the empirical variation from stranded power. So stranded power, so this is a stranded power we take from the ERCOT, so the Texas power grid, of a whole week in several different months. So the stranded power means the curtailment from the power grid or the negative price power that doesn't cost any dollars. So these are the power that we got from the stranded power. And this is one example of a whole week for the resource capacity. So we can see that with stranded power, it produces a binary on-off resource capacity over a short period. And so basically this represents a more extreme variation scenarios comparing to the other two. So there are a few metrics that are either system-centric or user-centric that we considered and potentially will be used in the future. So the first is good put. So basically it's a throughput of all the non-terminated jobs. The second is a failure rate, which is a percentage of jobs failed to complete. The third would be user-centric, so the average job wait time. And similar to this failure rate, there will be service level objective miss rate. So that measures the percentage of jobs failed to complete before the SLO deadline. And there are other metrics like slowdown, fairness, system constraint, etc. So for the demonstration of the evaluation, we will focus on the good put in this presentation. So some of the workloads that we use, so we consider three that have different characteristics. So the first actually demonstrated on the leftmost chart over here. So it's the Mira workload. So this is a trace taken from the Argonne National Lab Mira supercomputer. So it's a large scale HPC workload. And so if we look at the job attributes, so the y-axis represent the job parallelism in terms of node, and the y-axis represent the job runtime in terms of hours. So we can see that it has extremely high parallelism, with the smallest to be 512 nodes, and the largest to span the whole supercomputer. And the scheduling algorithm we use for Mira is taken from their original scheduler, is the compute utility functions and with backfilling. And the second is the Azure workload that is from Microsoft, and it's workload of cloud VMs. So if we look at the job attributes figure in the middle for Azure workloads, we can see that it's the maximum goes to 8 cores, and so it's rather low parallelism. And but some have have longer period of runtime. And so we use first come, first serve, first fit scheduling for Azure. And similarly, we have Borg. So it's a cluster workload from Google. And we can see that it has more, even smaller parallelism compared to the Azure workload. And similarly, we use the same scheduling algorithm. So we first want to look at the impact of capacity variation in a hypothetical 40 megawatts data center in Germany. So this is a system performance chart in good put, and we compare fixed with variable capacity. And the variability traces we introduced previously obtained by the constant carbon approach in the German grid. And so each cluster of bar represents a day in a month. And so we are comparing the fixed with the variable capacity. And so the traces have 24-hour capacity increase from 6% to 16% in terms of total usable capacity. And if we look at the experiment results in terms of good put between fixed and variable, we can see that there are large decreases in good put in most of the cases, and so up to 24% in the most extreme, and 12% on rightmost in average. So now, if we want to understand specific dimension of the variability structure, we look at dynamic range and variability structure separately. So first, this is good put measurement taken from the Hpc workload. So the x-axis, we vary the dynamic range from fixed all the way to most extreme, and then so we can see that as the dynamic range increases, the performance degrades from 15 to 28%. And now if we add random uniform to compare, we can see that random uniform have 35% further degradations compared to the random walk structure, because it allows larger jumps in capacity changes. And now if we put the Azure Microsoft cloud workload inside, comparing side by side with the Hpc workload, we can see that the cloud workload is less sensitive in terms of degradation because it has lower parallelism. And then next, we will look at the impact of change frequency. So this is a figure similarly measuring good put, where we look at different workload fixing one dynamic range. So within each cluster, we are looking at change of frequency from small to large. So here is one change of capacity every 4 hours, and here is 4 changes within 1 hour. So 15 minutes with the change. So we can see that within each cluster, as the frequency increases from left to right, the significant good put is dropping across all the structures and different workloads. But similarly for HPC, it's most sensitive, so it has up to 50% good put degradations, where for the Azure workload, it has only 15% attributable to frequency. And of course, Borg is even less sensitive compared to Azure because it has even smaller parallelism. So they are less sensitive, and also they have the majority of them have shorter duration, making them even more less sensitive. So sorry, I didn't forget. So we proposed a couple of scheduling policies that try to mitigate performance degradations. So the way that we are thinking is to select job to terminate with the goal of maximize good put. So we have a couple of different policies. So the first is random, and second is choosing the jobs that have the least fraction finished. And the third is choosing the job that has the least wasted work incurred. So the first is a Hpc workload, where we have varying each cluster, varying the different policies, where this horizontal line represents a fixed scenario for comparison. Similarly, we have Azure workload here also, measuring the different policies. So if we look within each clusters, we can see that the scheduling strategies provide improvements. So the rightmost bars comparing to the blue bars, so that it's actually, for the Hpc case, it's close to the fixed scenarios. And for Hpc, it has larger improvements for about 44% average, where the commercial cloud has smaller benefits because there's less improvement that needs to be done. So in summary, we define the variable capacity scheduling problem with 3 key dimensions. We provide realistic examples that can be characterized and abstracted into general problems. And these traces, we will make them available online. And we also show that scheduling performance can significantly degrade in the face of variable resource capacity from 25% to 50%. And last, over scheduling improvements shows great potential in mitigating the performance decreases with 44% increase on average. And I think with that, I will conclude my talk, and I'm happy to take any questions.
Thank you very much.
Thank you.
That was a beautiful timing, on the minute. Are there some questions? I was just wondering, I like the slide where you showed the impact these variations have on different workloads, and you show that HPC is very sensitive due to parallelism, right?
Yes, yes.
So my question is, but it maybe it's just a provocative question. I don't understand why we buy large, very expensive HPC machines for which we don't have enough power. I mean, is it reasonable to constrain HPC computations to some green energy constraints? If I don't mean like that I'm against green energy. I just don't understand why would someone buy a supercar and then wouldn't buy a petrol into the car. It's something that's somehow different maybe here in Europe, or at least in my country. If you buy a expensive fast machine, you should make sure that it's running to its best. So what is the approach to that in US or everywhere basically?
Andrew, you can feel free to jump in to make comments. So I think there are a couple of things that. So one is a lot of clusters, even large-scale supercomputers, they have. Of course, correct me if I'm wrong, but they first have hardware over provision. So basically that means you don't get to use all the hardware at the same time with all the power. So that's already kind of contradicts what you were saying, that why not allow them to use more power, right? So, and also another level I think is supercomputers are really large entities in terms of consuming power. And so they are one of the largest target in terms of constraining power. And there are a lot of studies on supercomputers that try to, or extremely large scale HPC computers that try to have power envelopes, like power capping. So what we are providing here is a more kind of frequent changes in terms of power capping. Because most of the power capping, they're fixed in terms of a long time. So we are considering a more extreme cases and more frequent cases, and potentially with enough scheduling improvement, more flexible cases, because you can temporarily have more power or a lot of more.
So I could just add, right? Can you guys hear me?
Yes,
So, one of the other motivations which Sam called out really is to try and reduce carbon emissions. And I think, I don't need to explain to the audience here that worldwide, there's significant pressure to reduce carbon footprint for all kinds of activities, not just computing.
To highlight it. It's clear, but...
Yeah. but I think that the interesting thing, a lot of people don't realize that how large computing has actually become as a fraction of electricity consumption in the world. In the US, we have some regions that are somewhere north of 6 or 7% of the power grid energy is actually being used for computing. And that's like Northern Virginia, for example, where there are a lot of cloud data centers. And in many of the US DOE, large computing facilities, the power is doubling, right, in the current generation, and may double again. I know from some inside data that the fraction of power consumed at the lab level, right, that the supercomputers are now more than half of the power at many of those labs. And, if they double again, they're going to be, 80% of it or something like that. So those are some of the issues. But I think another way of thinking about it is that the notion that we have to somehow run a supercomputer because we paid for it may be a bit of an old-fashioned notion, because there are many actually resources that we buy that are very expensive that we would like to run sort of all the time. but for other constraints, right, we don't actually run them sort of 24/7 full out. So there are some of those kinds of issues. But certainly for this community, I would say one other thing, which is we know we can change power consumption, as we just saw in the previous talk, just by doing scheduling, right, and workload characterization and picking the right jobs that run at the right time. So I hope this is a great opportunity for this community to try and figure out how to do some of that, right? So it's not about not utilizing the computer, it's using it better.
Part of my question, whether it's not the goal of the scheduling community to somehow organize the workload in such fashion that actually, because different types of workload requires different amount of energy, so maybe that may be a way how to approach this as well.
Let me give you an interesting case, Dalibor, to which I think we can make an argument we are not underutilizing the supercomputer to some definition. That definition is sometimes there is no load that is available for you to run at maximum utilization all the time. For example, Dror showed in his presentation a situation that during the night the queue would be drained, especially because there were no new submissions.
Here it was different. It was, jobs were killed because of energy.
So maybe I misunderstood the example that Dror gave, but there are situations that there is no load all the time. So you could potentially delay some jobs in a way that you will still run everybody, let's say, in 24 hours. People would get a delay. Which, not the best thing in the universe, but again, it depends on what you are going to do with the results. Sometimes if you are a researcher that you are waiting for the results to take a look, the delaying is not so good. But again, it doesn't really matter for you if your job finishes at 1 o'clock or 6 o'clock in the morning. You are sleeping anyhow. But even if the consumer of the result is another stage of the pipeline, that may not matter. So by delaying jobs, as long as there is not enough workload for you to be fully utilized, you may change the consumption to a greener sort of profile, which would be very interesting.
Yeah, it's just because it's a repeating topic, and I've heard these talks several times, and there is, I just need to better understand this. So
it's a fair question, because that's how the facilities people think. I would point out one thing that's also interesting in this space, and Sam has done some prior work on this with spot instances, and I'll just highlight, she has a paper in the upcoming ISCA that looks at some of these ideas in a cloud setting, which is the cloud folks have begun to think about having different levels of priority of workload. And if you have, in the scientific community, we have high throughput workloads and those kinds of things, you could easily imagine deciding to build tiers of load in a scheduling problem, some of which can be shed on short timescales, either because they're less valuable or because they're checkpointed or backed up in some way. And so I think that represents some interesting other ways of attacking this problem.
Yeah. If you allow me, I had a comment. I'm not super sold on the energy as the driver factor. I'm a little bit with Dalibor. I think all of us, especially these days, scientific and non-scientific community, everybody's super constraining capacity. Like my experience at LVNL was that the supercomputers were used all the time. It was just a matter of who's getting more queue time or less queue time. But there is something that it's actually very connected to this work, which is large infrastructures have periodic work that usually requires taking away sections of the capacity to do anything, from updates, kernel updates, and that can have a periodic pattern that could benefit from for processes like these, in which you make a scheduling aware that there's going to be a repeating event or semi-repeating event or kind of predictable event of reduced capacity. Imagine it works for, like in supercomputing, it is really sad because basically they take down the whole cluster to do upgrades because they don't have the ability to survive with a strong variability of capacity. and other people suffer from similar problems, right? And a scheduling system that is able to make placement decisions and take into account that some resources will disappear can be very valuable. Even if you're thinking about the choice of the node or which you're going to place stuff, assuming that you actually know which part of the capacity will disappear. I think there's value there. So maybe not energy driven. I'm not very sold on that, but I do see how large infrastructures have a strong variability of capacity that have a dynamic pattern that could be somehow predicted and could benefit from scheduling. And my rant is over. Sorry.
Well, our motivation, Sam can say this, but our motivation was to inspire some number of people to get excited about these kinds of problems. And, it's good, actually, that there's some notion that it may or may not be, indicative of all situations. Not everyone has to work on this, but we think it's an interesting direction for some range of systems. So,
yeah, absolutely. Okay. So I think we can somehow conclude this workshop. Do you have some feedback? We had 10 papers. Each of them was presented live, which is a miracle. We have very nice keynote. Thanks, Dror, again. And feel free to provide us some feedback. Did you like it?
And thanks for coming, staying and contributing, submitting papers and participating in the discussion. It's
absolutely
great to see everybody, even if it's like remotely.
So I think it's interesting. We definitely have had more people in the virtual room at the end of the day for the last 2 years while we've been remote than we would end up. I mean, we always had pretty decent attendance at JSSPP, but by the end of the day, everybody's kind of dragging. And having 19 people here at the end of the day is pretty good.
Yeah, I was periodically checking the numbers, writing them down. So the maximum was 25, but the people were changing. So yeah, it's nice. Maybe we should think of some remote attendance in the future as well, even when these complications related to the pandemic are over, because let's at least try that, because I think that for some people it may be a good way how to join us and attend the discussions.
So if I can say a word about that, the steering committee of IPDPS is currently thinking about how to make something like that happen. They are trying to think about what would it mean for the workshops and the conference to be hybrid. So if you have any ideas, feel free to reach out to Victor. The steering committee is definitely looking for ideas on what can work, what could work, and what's interesting.
Thank you, Eric, and nice to see you. Okay, guys. Again, thank you very much. If someone from the steering committee, Narayan, Alfredo, Gonzalo, do you have some final thoughts?
Let's thank Dalibor and Gonzalo, who did all the actual organizational work for this year.
Absolutely.
I think it's turned out really well.
It's 90% Dalibor anyway.
You underestimate your contribution, but thank you.
Very appreciated.
So it's been a pleasure, and hopefully next year we'll meet in Sweet France and drink some wine for real.
Yeah.
All right.
Together, drink wine together.
Yeah. Cheers.
We're drinking anyway.
Cheers for that.
Okay.
Thank you guys for organizing. Appreciate all the hard work.
Thanks.
You're welcome. I will be in.
Take a virtual picture of everybody. Let me do that. Hold on for a second. Let me see if I can change the layout to get everybody in. change layout.
And please don't stop. Please don't forget to stop the recording and save the last session, Alfredo.
Okay. Now everybody turn on your cameras and smile. Nice. We are going later on to post on the website.
That's a good idea.
Thanks, folks.
Thanks, everybody.
Thank you.
Thank you. Bye.
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 Bye.